So our next speaker is a graduate student here underneath Dr. Godden. Her name is Whitney Knauer. Knauer. Aaron told me wrong.
That's okay.
Knauer. And she comes to us via Pennsylvania and New York and now to Minnesota. The title of her talk today is The Use of Statistical Process Control Applied to Daily Average Feeding Behaviors to Predict and Detect Disease.
Thank you, Pat. So a little change from genomics. Those of you who have been here the past couple of years, I've presented more and more of this. So today I will peel back the final layer and give you the full picture of using feeding behaviors to predict and detect disease in group house calves. So traditionally, we have reared calves in individual housing, and advantages of this system we know are mostly disease prevention. So there's less nose-to-nose contact. It's easier to detect a sick calf, so we're going out to these calves 2 or 3 times a day, looking to see if they drank their milk, looking to see if they're standing for too long of a period of time, looking for that dull calf. But these systems are labor intensive. And so, especially in the upper Midwest, producers are more and more interested in group housing and computerized feeding of their pre-weaned dairy calves. And benefits of this, so it's easier to feed greater quantities of milk. You can program these machines, these computer feeders, to feed 8, 10, 12 liters of milk a day. There's not a reduction, but a reallocation of calf management activities. If you were here yesterday, you heard Sheila McGurk talk about, and Sandra Godden talk about how producers often put these in and then walk away, when in fact management changes. You still have to walk pens, you have to look at the computer, not a reduction reallocation. And then there's also this emerging benefit of these animals are able to express their natural social behaviors. They're able to be herd animals earlier in life. However, there are significant challenges to these systems, and the biggest one is that there's increased morbidity and mortality, and dairy cows are herd animals. They tend to hide their disease, and so disease detection in a group is just a little more challenging. And so currently, how do these systems, how does the software program help us detect sick animals? And so on a daily basis, there's a report that's generated looking at things like total consumption per calf per day, drinking speed, so how fast does the calf drink her milk meal, and then visits to the feeder. So we can look at rewarded visits, so when the calf goes up and actually gets a milk meal, and then unrewarded visits where the calf is either hungry or optimistic that she'll get a milk meal when in fact she doesn't have an allocation. And so these software programs, the Cow Manager, which is Forster Technic, which is Lely, DeLaval, and GIA systems, these software programs are designed to flag calves. So on this screenshot, any animal that has a red bar, that would be an animal that was flagged for the producer. And so this it's a deviation approach, so it's a 25% deviation of a 3-day average. And the question is, does this work? And so there's been some work done and the answer is not so much. And so this is a study that was done in British Columbia almost 10 years ago now, where they had 2 groups of animals. So they had a group that was fed pretty limited milk, so 4 liters per day, and then a group that was fed either 8 liters or ad lib. And this graph shows that, so the animals, so milk intake in liters per day is on the y-axis, sick days. Illness was detected on day 0 by a veterinarian, and then they looked at the 2 days before and then 8 days after illness detection to look at differences in feeding behavior. And in fact, the animals that were limit fed didn't change their behavior because they were hungry, but animals that were allowed a higher level of milk, which is more commonly what we see in systems here, those animals changed their feeding behavior, so they drank less on the day that they were detected as sick, but not before that. And so this is where it changes a little bit from what's in your slides. So the data set that I'm going to be talking about was a prospective study looking at 10 commercial dairy farms, 4 in Minnesota and 6 in Virginia. And we collected data over 9 months. And the important things here is that we collected treatment events and feeding behavior. And so we collected drinking speed, daily average consumption, rewarded and unrewarded visits. And so this is kind of a snapshot of what we found. So we wanted to repeat that work that was done by the University of British Columbia, looking at the feeding behaviors that we collected to see what the deviation was, the difference between matched, sick, and healthy animals. And so I'm going to show you 4 graphs, and the first one, daily drinking speed. So we have the feeding behavior here on the y-axis, and then days from treatment. So I matched these animals, sick and healthy animals, which sick animals are the hatched line, and then healthy animals are the solid black line, and matched them on the day of illness, and then looked at the 10 days before and the 10 days after an illness event to see how these feeding behaviors changed. And in all these graphs, the red arrow is showing you the day of treatment. So this is treatment, identification and treatment by a herds person. And so this is overall for all calves that had an illness event. So 352 calves, 176 matched pairs. And here you can see that overall, calves changed their drinking behavior, deviated from normal 2 days before a treatment event. And I identified, so diarrhea, ill calves, so these are calves that are treated for a fever or for the ADR, so the calves that don't quite look right but get treated, and then respiratory disease were the 3 treatments that I looked at. And so here are the results for drinking speed. So 2 days prior, diarrhea and illness followed that same pattern as the total population of sick animals. And then for respiratory calves, those calves had no difference in their drinking speed at any point during that 21-day period. And so daily milk consumption, so milk consumption in liters per day, a similar pattern. So on the day of treatment event, 2 days prior to, and then on the day of treatment, and then through the 10 days, sick animals had a reduction, a significant decrease in the amount of milk they consumed over that period. Calves with diarrhea followed that same pattern, respiratory calves and calves that had just an illness, other illnesses, no difference. And then here's daily unrewarded visits to the feeder. So when the calf goes up for a drink and she doesn't get one. So you can see that this changes, sick animals changed up to 4 days before a treatment event, and then that persisted through those 10 days. Again, diarrhea calves showed a similar pattern. Calves that were ill, those ADR fever calves, changed, but just very briefly around the time of treatment, and then respiratory calves had no change in their unrewarded visits to the feeder. And then here are rewarded visits, so this has no change. So sick animals, healthy animals, they go up to the feeder and drink about 4 times a day, regardless of whether or not they're sick. And so what did we learn from this? So sick calves have a reduction in their drinking speed, a reduction in their daily average consumption, and a reduction in their unrewarded visits to the feeder. And they, this happens up to 4 days prior to illness detection and then persists. And then this variation, this difference varied by disease treated. And so now I will talk more about how we're going to look at this data in a little different way than just the average and the deviation from average. And so I'll talk about it in the next slide, but we applied statistical process control techniques to these daily average feeding behaviors to see if we could use this different methodology to find this calf before a trained observer. And we hypothesized that indeed it would work and that we would be able to find a sick calf in a more sensitive and timelier manner. And so for those of you who are not familiar with statistical process control, I will explain it to you. So SPC is a analytic technique that utilizes the theory of variation to monitor how a process changes over time. So traditionally used in manufacturing and newly applied to biological systems. And so in essence, what we do is we're looking for abnormal variation. So this is a graph of a calf in a feedlot, and this is days on feed. And you can see that this animal, and time at the bunk, and so you can see that this animal has some variation, but we define an upper and lower control limit where we say, okay, if the calf goes outside of these control limits, then we have a signal, and we call the process out of control and we intervene. And so that's depicted here, where this animal decreases her time at the feed bunk, it goes over that control limit, which is basically a measure of sensitivity, and we intervene. She goes to the sick pen and gets treated. And so I did this for all of these calves for drinking speed, consumption, and unrewarded visits. And I did it in a couple of different ways. So feeding behavior is a little tricky because there are feeding plans. So this is an example of a feeding plan on one of our dairies where we have an increase, the calf enters the pen, we have an increase in milk, this is milk provided, up to 10 liters, and then she's held at 10 liters for a while, and then we decrease. And the same happens for drinking speed. So drinking speed increases over the time the calf is in the pen, so that can lead to false positives. So I looked at raw data, and then I standardized the data. And then I looked at different control limits. So remember that control limits are a measure of sensitivity of the SPC to signal. And so here's an example where we look at different control limits, and this can represent a calf and her feeding behavior. So we have a running mean, and this calf decreases her running mean, like she would if she had a decrease in her drinking speed if she were sick. And let's pretend that this arrow here represents a treatment event. And depending on where we put these control limits, whether it's at 1.5, where we might signal at 7 days, which would be prior to her being detected as sick, versus if we put these limits at 3, where we might not find that calf at all. So I looked at all kinds of different control limits to try to find the optimal parameters. And so I evaluated and compared these diagnostic test characteristics of a positive SPC signal to find a sick calf, and that I only looked at first treatment events in a testing subset of calves, which was the same calves that I looked at their feeding behaviors. And then, so my index test was an SP signal on a negative mean. Remember, calves decreased their drinking speed, their daily average consumption, and their unrewarded visits around the time of the illness event. And then our reference standard, or our gold, quote unquote, gold standard test was a first treatment event by a herdsman. And then I optimized my sensitivity and timing. We anticipate, if this worked, which maybe is some foreshadowing, we anticipate its use as a screening tool. So there's a flag on the computer for the producer. It says, okay, this animal needs to be looked at, go out in the pen and do a physical, look at the calf, and then intervene. So screening test. So we wanted to optimize the sensitivity of the test and the timing. And then I did all that with the testing subset and then applied it to all the calves in the data set. So 1,052 calves in those 10 farms that I described before. And then I looked at one signal, and then I looked at 2 signals in combination and 3 signals in combination to see if we had an advantage if we looked at multiple parameters, for example, drinking speed and consumption. And then I looked at them in a couple different ways, in parallel, combination, and series. So here are our results. So in this chart, so I looked at a lot of different things. I'm just showing you the best of the best, which you might look at these numbers and say, not that great, but these are the best combinations. And so for one signal, drinking speed had the highest sensitivity compared to consumption and unrewarded visits. For 2 signals in parallel combination, so what that means is that for parallel combination, it means that drinking speed had to be positive, consumption had to be positive, or they both did for that to be a positive test. And then 3 signals, so drinking speed, consumption, and unrewarded visits all together. And so we have an advantage when we go to 2 signals and sensitivity. So again, sensitivity is the ability of the test to find a positive calf. So if the calf is sick, the SPC also is positive. And so 1 signal, not much better than flipping a coin. 2 signals, 71%, not terrible. 3 signals, 75%. Then we move on to positive predictive value. So this is what you're interested in as a veterinarian. So what is our confidence that a positive test is a sick animal? And no real advantage with looking at any of these signals, either alone or in combination. And then we look at negative predictive values. So this might even be more important if you're using this as a screening tool. So this would be our confidence that a negative test is actually a healthy calf. And you can see these numbers, so 38% of the time we can have confidence in a negative test, not super good. And then, so we look at the signal relative to day of treatment. So one signal, we have that signal happening 2.8 days prior to a treatment event. Two signals in combination, drinking speed and consumption. So we have a 3-day advantage, 3 signals, it's happening on the same day. But I will draw your attention to the big range of those numbers. So we have, for one signal, we're looking at potentially that signal happening 46 days before a calf is treated, which isn't useful, right? Because you're not going to look at that calf for 46 days. That's silly. Although it's possible that that calf was sick and was missed. Don't know. And so, again, just because we have a mean of 3 days prior to treatment doesn't mean that it still doesn't mean that it's valuable. So, in conclusion, so using drinking speed and consumption in parallel combination was the most sensitive and timely when looked at those two things together, but these diagnostic test characteristics, the predictive values, are not sufficient to use this detection method alone, and the fact remains that we still have to look at calves when they're in a group. We can't rely on the computer either if we're looking at deviations or using this sort of methods. So, but I think there's still something there, so I'm going to continue to work on this to look at potentially other techniques or different parameters. So this is looking again at daily averages. So we also have the possibility of looking at meal level averages, which potentially could increase our sensitivity. But the main take home is that finding a sick calf in a group is still hard, and looking at calves is the best thing, walking pens, looking at calves. And so the big thing here, so funding, so the CVM Population Systems Signature Program funded this work. Our collaborators in Virginia, Bob James and Alyssa Dietrich, and then Doug Hawkins and Aaron Rendow for their statistical help. I'd like to thank them, and then I will take any questions that you might have. Oh boy. Oh good. So if I understand, your question is, these producers stopped looking at the computer. Is it because it was either overly sensitive or terrible? Yes. Yeah, so possibly. So that's the problem with using these types of data, is that it has to work, right? And one thing that I'm worried about, if we do implement some sort of algorithm, I mean, what I'd really like to do is apply machine learning to this and try to let the smart computer science people figure out algorithms that would update, and be iterative, so that we could get away from that. But when trying to adopt something new, especially if it's overly sensitive, you have a lot of false positives, it becomes a not useful thing. I think producers here in the upper Midwest tend to use drinking speed as the thing that they use, although most of them are also either go out and look in the pen first and then look at the computer to kind of back up what they're seeing, or the other way around. Nobody is treating based solely off of what they see on the computer. But I would imagine that it's probably, they look at the computer, they look at the calf, and they're like, that calf is fine. Why am I continuing to look here? I'll just use my calf observation skills. Well, didn't you read a paper about that last week, Baba? So there are other things. So we can use actual behavior indicators, right? So we can like walk up to the animal. So there's a paper published last year, or this year, sometime recently, where they actually walked up to the calves, and if the calves got up and ran away, then they said, okay, they're healthy, and if calves didn't, then they said, oh, they might be sick, and then they looked, it was a cross-sectional study, but the sensitivity was, it was 50%. So again, might as well flip a coin, because calves sleep 75% of the time, right? So, and also there are farm factors, so if you're actually walking through the pens every day, the calves are used to that, right? So walking through the pen is not a useful tool if you're considering the calf won't get up and run away from you. There are other things that have not been investigated, like activity, but for the same reason, because calves sleep so much of the time, nobody's evaluated it. But and some people say, especially so if you were here yesterday, you heard Sheila say that calves that don't feel well will tend to be standing for longer, right? So if you go through and feed milk and then you go through and feed water or offer water, and there are calves still standing after that, then that's a sign that maybe those animals need to be looked at. So it's possible that if we could measure standing in line time, that might be a useful thing. And they're also, so the company, so Forster Technic is actually looking at, they have sensors on the nipple, and they're actually measuring like force. So when calves get up to drink, right, they kind of hit the nipple, like they would, they're a cow, right, a cow udder. So they're looking at that to see if that's correlated. So there might be other useful things to look at. And I still think that this has value. I just don't think we're looking at the data in the right way. Yeah.
It's striking that the two lines are basically parallel and you can trace as far behind as you can. You think there's a possibility that more dominant calves are not inducing disease, but limiting to some extent the expression of behavioral axis, and that's why that's also affecting disease?
Okay, so the question is, why do unrewarded visits is there something else going on there? Are dominant calves affecting subordinate calves? Maybe. Another idea, so that's a hypothesis, another idea is that those calves that get sick are losers to begin with, right? Or that so these calves are also young, right? So it could be that calves coming into the feeder, they get sick day 7, 8, 9, so it could be that something else is going on before that that is affecting that behavior early on. Don't know.
The other one is there you always have factors not associated with the calf that might affect those measurements. Colder day, hotter day, management, personnel noise. Do you think there's value to include not only each calf deviation to detect this, but also some group averages as a baseline for comparison? So to use both, not only their own calf measurements, but also the group measurements to find the algorithm.
Maybe. Don't know. Good idea. We can talk about it later.